Good morning, everyone, and thank you for joining us this morning on this webinar on heat exchange. We hope that the time that you spend with us this morning is a good time investment for you, as I believe that it would. And we'll just be touching on general heat exchange topics through the day, bit of condensate removal and that sort of thing. The speakers for today, the main presenter will be Nick Wisby. He's the technical support engineer for the Kenyan operation. He started off his career in Spirax Sarco UK and is now based in Kenya in East Africa. Supporting Nick through this presentation is Wayne Tienison, who's the regional sales manager for KwaZulu-Natal in Spirax Sarco South Africa. And myself, I'm Cornelius Schenk. I am the national sales manager for Spirax Sarco, also in South Africa. So just in terms of housekeeping for this presentation, we are looking at keeping it at about 90 minutes. Everyone's mics will be muted, but if there are questions that pop up as we carry on, or some clarity that you may require, please feel free to just pop in a note in the Q&A session. Or there's a little tab on the right-hand side which says Q&A. So those questions will be seen by the producers, and the relevant questions will be published and answered where possible. We'll try and make a little stop after every section, see if there are any questions, and discuss those before we move on to the next session, if possible. It does happen from time to time, though, that we don't get to all the questions. We will try and keep those names, and provide, obviously it's not been posted anonymously, which is also an option. But we will try and reach out afterwards to you and try and get some clarity on those questions that you may have, for the ones that we may not get to through this webinar. The webinar will be recorded, and after the webinar, it will be available for you to download the recording, so you can actually go through it again at your leisure, or if there's something you want to just get confirmation on, or whatever the case might be. Please also remember to fill in the feedback form afterwards, because if we get feedback from people we present these webinars to, we can continuously improve that and continuously give you a better product in terms of these webinars. And additionally, just from my side, if there's something that catches your eye through this webinar, and there is something that you might want to explore a little bit further on your plant, something that you may not have been aware of before, and something that might be new information for you, please reach out to your local Spirax Sarco sales engineer. We will make a plan to get to the site and help you try and at least identify what the problem might be, and potentially also find a good solution for it. So Nick, Wayne, thank you very much for both of you, and for Debbie for setting this up. Let's get going. Thanks, Nick.
Thank you very much, Cornelius. So hello and welcome, everyone. Today, as Cornelius said, we're touching on heat exchangers. So first, as we do with all our webinars, we'll start with who Spirax Sarco are, then the types of heat exchangers available on the market, some heat exchange theory for you to be able to calculate the correct heat exchanger for you, and control methods and store. So who Spirax Sarco are? So all the blue areas is where we have a presence, the green ones too. We have 145 operating companies and 180 plus local sales offices in 55 countries. We're over 10,400 employees. I think now it's probably closer to 11,000, probably just over, and 2,000 plus local service. We have 29 manufacturing sites across 4 continents, and our HQ is in Cheltenham, which is in the southwest of the UK. And we have 59 customer training centres. So under the group, Spirax Sarco Group, we have the Spirax Sarco company that we're currently talking to you from. We also have Cotopaxi and Gestra, Chromlux and Thermolux deal with our electrical wing. Then we have Watson Marlow. We were founded in 1888, and we're a FTSE 100 company with a turnover roughly, I think it's a bit higher than this, but roughly £1.4 billion a year. So some of the products we offer, so as you can see here, we do boiler controls, flow metering, heat transfer solutions, so heat exchangers like we're speaking, steam traps, which everyone knows us for, We also do valve reconditioning, health and safety compliance, installation and commissioning, various other services. And we know what we're talking about. This is our boiler. It's based in the UK in our training centre. So when you attend a course in the UK, we take you through this boiler, we open it up, we run tests on it, we show you how to do it on practical tests. So it's not just theory. So types of heat exchangers. So we have three main types. We're going to cover all three and common applications. So first, this is a shell and tube. So as you can see, you have the liquid coming in from the left, being heated coming out of the bottom. Then you've got the outside shell, effectively, which is the media that's going through. So advantages and disadvantages to a shell and tube. So these are designed for higher pressure and temperature and power capability. Readily available. These things tend to be manufactured by many different manufacturers. They're very simple because of the thick material they use, the way that they're built. They're quite rugged, quite tough. A very close temperature control, so it can be very accurate, and low cost per kilowatt depending on the materials. So depending on what the materials of the shell and tube are. Disadvantages: heavy with a large footprint, so these things tend to be quite long. High costs for non-standard materials, so when you go away from carbon steel, stainless steel, so if you go to sort of say annealed steel, those kind of things. Rigid construction, so not suitable for flooded semi-flooded operations, so these things have to be completely full. And high thermal mass, so slow to react to rapid load changes. So shell and tube, some of the examples you've got here. So we're showing the coils and the tubes that are inside. So modified shell and tube. So I think we call this our Turflow. So these are good pressure and temperature power capability, simple construction. So they're a little less complicated than the standard shell and tube. Higher heat transfer rates, so it's more compact. And the high internal velocity, so self-cleaning. We will cover velocity later, so why that's important in a heat exchanger. And relatively low cost per kilowatt. So disadvantages, they are sealed, so you can't open them up for maintenance as such. You are relying on CIP and manual cleaning and fixed nozzle positions. So the Turflow heat exchanger, so as it says here, we've covered these already. High efficiency corrugated tubes designed to improve the heat exchange rate. So that increases the surface area to be able to transfer heat. Minimal downtime, so where it says self-cleaning with shell and tubes and Turflows, it's because you create a turbulent flow inside. That tends to break off any particles that may be forming on the tubes, so we say that it's self-cleaning. They're reliable and durable, so they're made of high-spec materials, which means they tend to last for a while. They are more expensive, but if you buy an expensive car, you don't expect it to break down. And they're flexible installations, so they're more compact than the standard shell and tube, so it's a little bit shorter, allows you to put them either vertically or horizontally. So stability and thermal efficiency. So with the turbulence, as we touched upon earlier, these things are designed to create turbulence inside the tubes. So that not only allows you for self-cleaning, but it also helps with heat transfer. So promotes greater consistency of heat exchange, as it says there. Easy maintenance, straightforward corrugated tubes, so no bends, nothing to try and get around while you're cleaning it, and space saving, as it said before. So they're made of 5 parts. So you have the outside, which is the shell, one, as you can see. The expansion bellows, part number 2, so that's for as it heats up. The shell connection flanges, which are on either side and top and bottom, and the tube side flange, as you see there, in the corrugated tubes, which are in the center. So these are designed to introduce turbulent flow purposely, so it increases the heat exchanger efficiency. And there's no gaskets, so I'm only going to touch upon this because we've spoke about it quite a bit. So advantages of a turf flow over a plate and frame. So we will cover the advantages and disadvantages of various different types. So as you can see here, the materials are stainless steel compared to the normal carbon steel structure of a plate and frame. Gaskets, there is no gaskets. There is gaskets inside each plate or over each plate on a plate and frame. The thermal expansion, so it's through the bellows that's on the body. The gaskets are one on the plate and heating on the plate and frame. Maintenance is minimal because you can CIP. You need to, on a plate and heat exchanger, you need to periodically replace the plates because of corrosion, erosion, broken of gaskets. Scale, so they're less suitable for due to corrugated tubes, susceptible, sorry. So because you have a straighter flow path, there's less scale that can be formed on the pipes. Durability, so they're high durability compared to the medium-low of plate and frame. And operating conditions allows for operating differential pressures greater than 10 bar, whereas you're limited to about 10 bar on a plate and frame. There is some that go slightly higher, I believe, but not much. And the cost to use practically zero. So what it's saying there is when you talk about the maintenance, the repair, all adding all those prices, there's a cost to use. Whereas a plate and frame has that cost because you need to replace the plates, the gaskets, so on. And the unit sizes. So the smaller size, you have bigger footprint on a plate and frame. Are there any questions at this point? Cornelius, is there anything there? So I'll carry on because
Nick, no
yeah.
questions, eh? You may carry
no
on.
problem. Thank you. So advantages again over the turf flow in the plate and frame. So the delta P between steam and water side is greater than 10 bar, whereas you don't get that because you can't have the pressure on the plate and frame. Maximum temperatures can be higher, as you can see there, and the minimum mechanical stresses. So because of the flow paths are relatively straight, there's no hammer, no wear on the joints, turns, those kind of things. Product sizing, turf flow tends to be exact size, whereas you can oversize, or you have to oversize a plate and frame because you can't get half a plate. So that's the turf flow. So EVC is kind of an expansion on the turf flow, so it's an exhaust vapor condenser. So this would be a typical system for capturing an EVC. So as you can see, you have a CRU, so condensate return unit. As most of you will know, you have a flash off when it comes from your air vent. By putting an EVC on the top, you can capture that vent, that flash off, and you can reuse it for heat. So you can recapture the heat before you lose it out of the vent. So typical systems, you have the vertical and horizontal design. So as you can see on the first image, to the right-hand side of the image is the turf flow with your supporting equipment such as traps, control valves. And then on the image on the right, you have a horizontal version where you have the heat exchanger through the middle. So shell and coils. So actually, just before I move on, any other questions on the shell and tubes?
Nick, there's no questions so far. Everything's good.
No problem. So shell and coil, it's a similar design to the shell and tube, but instead you have a coil inside there. So advantages, they're tightly wound corrugated coils, means you can fit a lot in there, means high heat transfer rates. Steam flow through the corrugated coils is smoother, capable of subcooling condensate, relatively low cost again per kilowatt of steam. So the disadvantages, again, these are sealed units, so they're difficult to maintain. Pressure and temperature limitations. So onto a plate and frame. So as you can see on the video here, this is the design of a plating frame. So you have the frame, which is the blue, the plates in between. Liquid comes through the plates, heats up, spreads through the plates, and then back out. You have your media, your secondary media, which you're trying to heat. The other side of the plate, you have the heat transfer coming through on the other half of the plate and through. So it's very simple design, very easy to fix when they go wrong, if they go wrong. So again, here's the flow principle. So you got your primary in red, your secondary in blue. So carrying bar, frame plate, stub bolts, tightening bolts, all of those are the frame. Then you have your plate pack in between and your guiding bar. So your pressure plates at the far end and your support column. So relatively simple, easy to pull apart. So advantages, these are compact and light with small footprint. Non-rigid construction allows for semi-flooded operation. So low thermal mass provides quick reaction to sudden load changes. So if you have a system which is up and down, these things are better than the shell and tubes at dealing with them. High heat transfer rates because you have a high square area because of those plates. Easily disassembled for cleaning and inspection. So as we showed, you just undo those bolts, pull the plates apart, the frame apart, get to the plates and slide them out. Disadvantages, so they're quite high cost in comparison to other solutions in the market. Fixed nozzle positions, so you can't move anything on there. Limited pressure and temperature range, because as we said, these will only go up to about 10 bar, slightly over some units, but not by much. And gaskets need replacing at regular intervals. So benefits compared to a shell and tube, so we've gone the opposite way now. So it requires less floor space than a shell and tube. It's less weight, they're smaller, and the installation is relatively easy. So as we can see here, so you've got the weight ratios as well to show you the difference. So do we have any questions at the moment? Yeah. No. So fatigue, when we talk about fatigue with plating frames. So thanks to the elasticity of the gaskets, as it says here, there will be no thermal fatigue problems in the PHE. So that's plate heat exchanger, plate pack. So yeah, the expansion, the retraction, things like that, the gaskets are designed to take that stress. They will wear out. So depending on the usage of your heat exchanger, we would recommend inspection probably every 3 to 4 months, replacement of those gaskets every 6 or 12 months. Again, it's very process dependent. If these things are being heavily used, you'll need more maintenance schedules. If they're relatively constant loads with little or no fluctuation, they're going to last longer. So temperature control accuracy, so low hold up volume. So effectively it's saying that it follows the set point very well. And the weight provides a short response time, so it's quick to react to different loads, and has a very high and accurate temperature control. So the reliability benefits compared to shell and tube again still. So reliability for the lifetime of systems. So it's effectively saying it's reliable. It's well documented how these things will react on all processes. So you can plan maintenance. You can tell the lifetime of the heat exchanger, or you can do a very good estimate. Quicker and more accurate temperature control. So again, as we said before, these are quick to react to sudden load variances. So they will bring temperature up very quickly compared to a shell and tube. No scaling problems, so they're unlikely to foul due to the design, the flow paths. Lower maintenance requirements and easy to service. So types of heat exchangers, so for manufacturing ones, so complete range of plate heat exchangers, gasketed, semi-welded, fully welded, electric, and unique ones, so ones that are on special order would be stainless steel, titanium, and graphite. So brazed heat exchangers. So before I move on to brazed, is there any questions on plate?
Hi, Nick.
Yeah, hi.
Yeah, we have a very interesting question. I'm not sure if it's a quick answer though, and it might actually be answered maybe after the call, because for me, it's actually an in-depth question, and it could result in the specific heat exchanger experiencing a stall condition order. I'm going to read out the question.
No problem.
I am answering it as in, I think you might cover this further down the line, but Abdi is asking, we're experiencing challenges with our plate heat exchangers in terms of thermal consumption and heat transfer efficiency. Specifically, we have observed higher than expected thermal consumption, which indicates that the system may not be operating optimally. Despite setting the desired inlet and outlet water temperature to 75 degrees and 85 degrees Celsius respectively, there appears to be an imbalance in the steam and water flow rates through a PHX. How could we determine the proper number of plates for the optimal heat transfer and safe consumption? Now, just the reason for me this is quite an in-depth question is that we need to understand if this is a trapped heat exchanger or if this has got a APT, automatic pump trap. Because for me, if you're heating anything below 100 degrees Celsius, we're probably experiencing a stall condition on this heat exchanger. I'm not sure if you want to interject there and maybe give an answer as well, or we could come back to this.
So I think it's going to be an individual process question. The first, I'm just like you, the first thing I would be looking at is stall. So see how if that heat exchanger is flooding, especially because you've got the sub 100 temperatures there.
Yeah.
It would need to look at the process to be able to tell properly. But normal sort of fault finding, first place would be traps. Is it trapped? Is it pumped? Is it flooding? Is it stalling? Those kind of things. So they're the first things to look at. Relatively simple to look at as well. And then you look at the sizing, the flow paths, the quality of the steam, and so on.
I think it would make sense for me that a specific Spark Soccer sales engineer go out to this plant and do an investigation with the customer into uncovering the entire system and what could be the issues.
Yeah, so certainly if you pass your details on to us, we'll get somebody out to you, we'll have a conversation and take a look at your actual process. So rather than it be the generic training that we're giving here, it will be specific to your heat exchanger. Any other questions?
Yeah, it's same gentleman's asking, can you please define how pressure drops affect PHX and optimal pressure range?
So pressure drops. So when you talk about the heat transfer or when you're talking about the flow through a heat exchanger. So when you've got you need a pressure drop to have the flow of the steam, as in any steam line. There is the situation when you have stall is when your pressure drop actually gets closer to zero. So you end up with a back pressure, but normally caused by a control valve before the heat exchanger and its closing. So I'm trying to think, are they talking about the transfer of the heat between the two primary and the secondary, or just the mechanical mechanism of how a heat exchanger works?
I think it's just around the way how a heat exchanger works in terms of pressure drop across the plates.
Yeah, so in every steam system, even a heat exchanger or any piece of equipment, you need a pressure differential across it because you need to have flow. So that gives you your flow. The transfer is from the enthalpy, the heat of the steam, so flooding through radiating through the plates into your secondary media. So the differential is more just to keep the flow through the steam through the heat exchanger. The enthalpy is what's actually transferring the heat to your media. So it's the pressure and the temperature of your steam, which is more important than the pressure drop across the heat exchanger.
Great.
Hopefully that answers it.
Yeah, hopefully.
Yeah.
Another question, yeah. What factors should be considered when selecting the material and configuration of the plates in the plate and frame heat exchanger for specific application?
So mostly steam is sterile. It doesn't tend to carry anything. When you're talking about the quality of your steam, the particles you may have hanging in it. So trapping, strainers, things like that before. You want the quality of your steam as high as possible. When it comes to the actual materials, it depends on the CIP you're using for that heat exchanger. So it will be chemical compatibility with the secondary media you have, but also CIP. So steam doesn't care what material it is really. It's more to do with the secondary and the CIP chemicals themselves.
Yeah,
so it's compatibility. Yeah.
I would agree with you there. No, I would agree with you there. And for me, I've done a lot of work on CIP heat exchangers, and for me, gasket free, like a Turflow, is the best option. I would try and steer away whenever you've got a caustic or acid from gasketed plate type heat exchangers.
Yeah, exactly that. It's always CIP or secondary. So steam is neutral. It doesn't really cause any damage to gaskets. I mean, obviously there's heat, but there's the media you're trying to heat and the CIP you use to clean it that causes the issues. So it's just the normal chemical compatibility charts on that. And as Wayne said, quite rightly, the shell and tubes are better positioned for heat transfer as long as you can get away with a steady load if you're using CIP. Any other questions?
No, that's it. I think we're all good.
So these are really great questions. So
now there is one more. Sorry. So can you please explain how multiple passes work in a PHE? Maybe you have a video. We've shown the video. Maybe we can just share that video. That video is on our website, isn't it? It could be.
It is indeed, yeah.
Okay.
Also, if you reach out to us, I can share the slideshows so you can go through them at your leisure, as well as the recordings too. So I can maybe go back and see if I can just show it again. So again is the video, so hopefully it'll play. So as it shows here, here's the passes. Yeah, so there's your plates. So there's your secondary side at the bottom. Well, sorry. Yeah, so I'm just waiting for it to get to the point. So primary in, heat across the plates. So as you can see, it's every other plate. And then your secondary in. So the transfer is between the radiated heat into the plate that the secondary is holding and transfers that way. Again, like I said, I can share the presentation and you guys can go through it at your leisure. Hopefully that answers that question.
Yeah, and I think we can then continue. Thanks, Nick.
No problem. These are great questions, so keep them coming in. So brazed plate heat exchangers. So the advantages, so these are very compact. They tend to be very small. You see these quite often in dairy and pasteurizing, so on. A small footprint. These are low cost in comparison to the others. Smaller, often in this world, means cheaper. So that's why they're low cost. High pressure, because they're brazed, because they're welded. They are capable of dealing with much higher pressures than standard plate and tube or plate and shell. Plate and frame. And disadvantages though, cannot be used when condensing steam applications. So if you're condensing the steam that's in there, it's going to give you a problem on this. They're very susceptible to flooding, to stall. Also, kind of the expansion of fluids causes a problem with these. Cannot be opened and inspected. So again, as we said, these are sealed units. So once they're done, they're done. They don't tend to show you there's a problem until they start leaking. And then by that point, it's a replacement. There's no service you can really do on these. And again, the nozzle positions are fixed. So plate and shell. So this is another kind of different type of the plate and shell. So with these particular ones, you have a large pressure and temperature load range, compact and light with small footprint. So these things tend to be very small. Can operate on semi-flooded, so these things don't really mind a bit of stall. we'd still recommend that you keep still to a minimum, or at least as wherever possible. And you can use the exotic materials on the secondary side without need to use them on heating. Disadvantages: standard units cannot be opened. So again, these are sealed units. High cost for openable units. So the serviceable units are quite expensive because of the design on these. And they have limited cleaning capability. So as we show here, we've got the plate and shell. So you've got the plate and frame in the top left-hand corner, and in the right-hand corner, the shell and tube. It's kind of a mixture of both, which makes the plate and shell. So they're designed for high pressure, high temperature, no gaskets again. So again, with chemical compatibility, it's not an issue. They're compact, they're relatively small for what they're designed for. Low incrustations, so effectively there's not much build-up scale and things. And temperature approach, it's quite easy to get these to receive temperature and at a steady rate. So FREM, so all we mean when we say FREM is flash recovery energy recovery equipment. That's wrong, I think. There's too many recoveries there. So this is just effectively recovering the flash from your heat exchangers, recovering the heat before you take it to drain or take it to elsewhere in the plant. So as you've got a standard layout here for a FREM. So as you can see, you've got your feed tank in the top left, you've got your heat coming through, FREM collects it, flashes it off, brings it back in and returns the heat back to either a heat exchanger or can be back directly to process. And then you're off to your boiler. And that's kind of roughly what they look like. Well, it's not roughly, that is what they look like. So do we have any questions before we go on to the theory?
No, so far so good, Nick. We've covered most of the questions. Thank you.
No problem. So this is where it gets a little heavier, so I'll slow it down. We're going to talk about the formalization and how you work out the size for these. So heat exchange theory, so as it says here, the kind of energy passing through bodies. So you have two different types. You have I can never say these, I'm sorry, microscopicity, continuous motion of atoms and molecules, so that's your kinetic energy, and macroscopicity, which is the transfer of part of the inner energy as heat, and that's thermal energy. So thermodynamic equilibrium, so characterization of the thermal condition of steam, of the system, measurable in a physical quality, so your load, gives you your temperature. Two bodies in contact with thermal equilibrium, so this is your transfer, and their temperatures are identical and constant, so no cooling, heating. No heat exchange can happen between two bodies of the same temperature, so there's no exchange of energy. You have to have a pressure differential across a heat exchanger. So types of heat transfer. So maybe these should have been closer to the beginning. So we have three different types. You have conduction, radiation, and convection. So if you think about a saucepan, as you can see in the image there, conduction is when the heat reaches the handle, starts to get hot. Convection is the flame underneath heating the media, and then radiation, so the heat you can feel from the fire. So heat exchange theory, again, conduction. So direct contact with molecules. So the flame is actually touching the thing you're trying to heat. So as you can see on the right, you have a piece of metal or something conductive like that. The flame is lapping, is touching the material. So that's transferring heat directly. No sensible motion of media, so it's not moving. And the kinetic energy transfer from molecules is at higher temperatures because it's direct. So radiation, as we speak of radiation heat, radiated heat, means no direct contact between bodies. So in this particular case, there's no contact, no touching between your hands and the fire. Electromagnetic waves effect, so it's the radiant heat by the heat of the energy released by the fire through the conductive body. In this case is the air, so warming the air and then radiating to you. Light fragmentation mechanism with different wavelengths. So in other words, it's not constant. There is ups and downs. There's more heat at sometimes, less out of it. Transfer is possible also in a vacuum. So you remove the air, you will still get the release of that energy around it, and it will still radiate. Hence why the sun works. Convection, so this is the final type. So it's energy transfer resulting from the combined effects of matter mixing and conducting. So effectively the convection was the one we were talking about with the liquid, the media inside the saucepan. So heat flow associated with the matter, so a flow in a fluid. So effectively the radiated heat was heating the pan, convecting through the material, so transmitting through the material into the media. In that particular case was water. So efficiency mainly linked to the fluid in motion. So the more movement, the more turbulence you have in that fluid, the more transfer you have. So if you think about a kettle, when you start to boil it, you hear the noise of the kettle first start. There's little movement to that water. It's slow to heat. As it gets close to boil, it becomes more animated, more turbulent because of the bubbles that are collapsing inside. So you get more transfer of heat towards the end than you do at the beginning. Any questions at this point?
Nick, there's no additional questions.
Okay. So heat exchanger. So as we're using the turf flow here to show, just because the image is smaller. So primary fluid entering at the top, process fluid coming from the right hand side. So your shell edge is your primary fluid, the tubes in the middle are once being heated, and then your condensate cooling water. So it's effectively the condensed steam you've had coming in on your primary fluid, coming out the bottom. So Reynolds number, so RE. So this is the theory behind it now. So Reynolds noticed that when he was coloring the water, linear paths had low velocities, whirls and whirlpools had high velocities. So we will cover what that means and why it's relevant, whether it's effectively the number ratio between the forces of interior and viscous forces. So effectively the difference between linear and turbulence. So we can classify flow in two different types. So as we said, laminar or linear flow paths within a flowing per concentric cylinders. So these are all based on a cylinder design. So a tube, a pipe, and turbulent flow. So non-linear, it's not straight, interrupted by whirlpools, by various different currents that are in there. So RE is related to the transition and in the flow regime of the constant. So effectively, it's the transition between laminar and turbulent flow. However, the fluid in the pipe diameter is defined by, so here we have U, it's not U, it's UMA, isn't it? Equals dynamic viscosity of the fluid. W equals critical velocity. Delta bar P equals density of fluid, and D for delta is the piping diameter. So we can use that as RE equals WdP over U equals WD over V. So any questions at that point?
No questions, Nick.
So how can we use that formula? So we'll expand on that now. So each fluid has a value of critical velocity, which identifies its transition. So effectively, when it moves from laminar to turbulent flow. So if we take that same fluid formula that we used before, rearrange it slightly. So here we have U is the dynamic viscosity of the fluid, P is the density of fluid, piping diameter, just as we had before, gives you the WC, which is your heat transfer. So we have here 4 different conditions can be identified using the RE value. So RE here is greater than 2100, so it's laminar flow. So as you can see, you've got the formula there. We will expand on these in all sections. So if I don't touch upon all of it, it's only because I know we're expanding on it in a later slide. So how does that relate to a heat exchanger? So if we give labels to the primary and secondary inlets and outlets, so we have T1 and T2 for your primary in and out, your process fluid T3 and T4. So we can use that for Q, so Q equals MC delta P and over time, so T. So again, I'm going to show that, but we're expanding on it. So I'm not going to go too much into it right now. So here is the formula that you saw on the previous page. So you have CP, which is your specific heat, so your kilojoules per kilogram of steam in your heat or your heat. M is your mass flow rate, so kilograms in second. And your delta T is your time out minus your time in. So again, more of an expansion on that. So we have CP again, these values are not changing. So it's your kgs per kilogram of heat, your mass flow rate, heat transfer. You guys can read just as well as I do, but we added the A for the square area, the surface you have, and delta T MLN. So that's the logarithmic mean temperature difference. So the difference in temperature between your T1 and your T2. Any questions at this stage? No? Okay.
No
so what does that all?
No
problem. So what does that all mean? So the MLN is the most important parameter when it comes to the previous formulas and for formulas for heat exchangers, because it's the value that influences the geometry of the heat exchanger. So how many plates you need. So you can increase U delta T and decrease MLN. So as it shows here, it depends on the configuration of the fluid inside the heat exchanger. So you have co-current, counter-current, so effectively the flow directions you have. Again, where I'm only touching upon these is because I know they expand on in later slides. So logarithmic mean temperature difference, so the temperature difference you have between your primary and your secondary. So there is a direct effect on heat transfer rate depending on the relative layout of the hot and cold fluids. So by knowing the gap between your hot and your cold, you can calculate the size of the heat exchanger, the area that you require to pass the heat, to transfer the heat and give your secondary up to the temperature you need. So here, as you see, you have delta T MLN equals delta T of T1, so your primary inlet, minus delta T of T2, so that's your primary outlet. You've got IN, and again, delta T of T1 divided by delta T of T2. So co-current. Flow lines of hot side and cold side are maintained parallel. So effectively they match, as you can see on the picture there. They are almost a mirror image of each other. So along the surface of the heat exchanger. So there will be a surface in between where these meet, and that's where it's just saying. The outlet temperature of the cold side may not exceed the output temperature of the hot side. So you will not get your secondary fluid to be hotter than the primary fluid you put in, or primary media. And again, so you got an example there of temperatures there. So you got delta T1 equals 160 minus 90, so that's the temperature differential, equals 70 degrees. Delta time T2, so you got 130 minus 110, gives you 20 degrees. We can use those figures to put delta T MLN, so it equals 70 minus 20 over IN, which is 70 divided by 20. Equals 50, gives you the figure 1253 there, and it's equals or above 39.9 degrees C.
Nick,
yep.
Just something that's come through, is T not temperature, and I think you said it was time. Is T temperature not time?
It's temperature, yeah, sorry.
Yeah,
it's just yeah. Sorry about that. I was
no problem. Just confirm.
Thinking ahead of myself, yeah. So again, another formula there. So this is for countercurrent. So again, you can see the difference in the flow path there, the difference in movement there. Yeah, so in this particular case, as the example we've used here, got delta T1 equals 130 minus 90, so your temperature differential there, 40 degrees, so it gives you 40. Delta T2, 160 minus 110 gives you the 50. And again, you guys can read, so I will leave the rest of the formula. You can see the example there, giving us 44.8 degrees C. So to sum up, co-current and counter-current. So as you can see here, in which case the heat exchanger is smaller. So which one would be smaller? It would be the, company confidential, I forgot to remove from there. It's not actually confidential. So I'll leave that one for you. So typical application for a turf flow, steam and shell. So we've got saturated T1 and T1 on the bottom there. So saturated liquid. So you've got the energy there, T1 equals T1. Energy and the steam has lost results of latent heat. So it's been from saturated steam to a liquid. So it's given up its enthalpy, given up its heat and changed phase. Have we got any questions? I don't know if I've given enough gap there.
Yeah, just a comment. I think you keep saying time and not temperature.
Temperature. Sorry, it's sorry. It's I'm currently sat in Tanzania, so many things happening around me. I should concentrate a bit more. So in case here we have the hot fluid yields a heat by condensing, so giving up its enthalpy at constant temperature, e.g. water vapor, and then logarithmic mean temperature difference does not depend on the relative flows towards. So you have there the delta T mean counter minus the current equals delta T MLN co-current. So logarithmic mean temperature difference. So again, just the formula there. So you've got Q equals, it's not M, I can't remember what the symbol is, but it's MC delta PET equals UAT MLN. So in a nutshell, as it says here, condensing the same inlet temperature, counter-current flow requires lower installed surface, so than a current flow one, so it's a smaller surface. Condensing the same delta T, so higher inlet temperature requires a bigger installed surface, so you need more square area. Condensing the same inlet temperature, higher delta T requires a bigger installed surface again. So practical example. So here we have a problem. So heat 10 meters cubed an hour, from 70 degrees to 90. Availability of steam is at 10 bar G. So by using those, we can go into the formula below. So Q equals MC delta P T equals 200 or 2,000. KCL over H, so time. And you can see the example that works through there. Any questions on that example?
None coming up there.
No. So another one, which is required to be the primary steam mass flow rate. So here you have H is equal to or above 500. So you've got kcal over kg per degrees. Evaporation, condensation, enthalpy of steam. So again, we got an example there. The reason I'm not going through these examples is because they're shown on the screen. So you guys, if you have any questions further, we can go through the calculations in depth. This is just more to show you the formulas that you can use. So you can watch the videos and be able to calculate the loads for your heat exchangers needed. And then we can, I think we have a deeper, in-depth theory planned for later in the year.
Nick, there is a question here. I want to know, where is the implication of the Reynolds number so far in the calculation?
So I don't think it really shows on here. So the Reynolds would be the difference between the types of heat exchanger, if I'm right, isn't it, Wayne? You probably know this bit a little bit better than I do.
Yeah, generally based on the velocity through the tubes, I mean, we use it a lot when sizing turf flow because we want that self-cleaning effect. If you've got a low Reynolds number, which gives you a laminar flow. You're not going to get that cleaning effect. And the heat transfer obviously is affected,
Yeah, so it's more, yeah, so again, it's like you said, it's for the cleaning. It's more to do with the type of design that you choose rather than the formalization to work out the size of the heat exchanger. I think that's right. So as you was, yeah, like you were saying with, yeah. So hopefully that answers that question. Any more?
There is another one. It says, is there literature available for the U values for the different HTR types? Do the U values take into account fouling?
So I believe we have it listed on our website. I know we do have in the UK. There is literature there. We have the engineering books. SA, you probably have it on yours too because it links to the homepage, yeah?
Yeah, I'm not 100% sure, hey?
If you send us a request, we can do some digging. We can find that information for you. So at the end of the training, if you supply your contact details with the question you have, with the literature you require, we'll try and find it and send it through to you.
Yeah, this has come up as anonymous, so we would need details.
Okay.
Yeah.
So process data. So for basic data for the description of fluids. So here you have the density, so kilograms per meter cube equals FT. Heat capacity, so CP. And you have the thermal conductivity, which you also need to know. And then the kinematic velocity, so the way it's moving through the pipes. Basic data for the description of the process. So this is the minimum requirement you need. So you have your flow rate, meters cubed per hour, inlet temperature, outlet temperature, and your duty. So again, that gives you the formula you can see for both. So below. So heat exchangers and control methods. So this comes to stalls. So this covers I think there was a question earlier on when they were talking about a process to be able to tell there was a high thermal demand on a heat exchanger, I believe, wasn't there, Wayne? So yeah, so provide a required degree of accuracy. So this is why we need to make sure we have a good control method in place for our heat exchangers. Be reactive to the secondary load requirements. So as that changes, as it goes up, as it goes down, we need to be able to adjust our heat exchanger to be able to make it as efficient as possible. To be safe. So without control, there's no control of the heat that's being transferred between your two medias. Make full use of the energy available in your steam. So steam is expensive to manufacture for us, so from your boiler, from the materials you need to heat. So we want to be able to use as much energy out of that steam as possible and avoid energy waste, so flash steam as it says here. So again, another formula. So here we have CP equals the specific heat, so the kilojoules per kilograms. M is the mass, the mass flow rate. U is the heat transfer coefficient, so how much energy it's going to give up. Surface area is A, and then you got the delta T MLN, which is your logarithmic. We'll learn to say that properly. Medium temperature difference, so the differential. So you can adjust these down to give you the results you need. So it's just an expansion on the control actions. Basic control methods. So as you can see here, we have a heat exchanger, you have your control valve, you have your secondary out, and your condensate being sent out the the outlet of the primary side. So example here. So whoops, sorry. So here we have steam pressure at 4 bar, condenser power is 1046 kilowatts. And as you can see, we got the 1.5 bar A out, so it's all in bar actual. And so the list of parameters there in the right hand side. So how we use the formula. So as you can see here, Q equals UA delta T and MLN. I think we do have the actual example somewhere. I'm just going to skip through this because I can see we're running out of time. So So stall in heat exchangers. So I wanted to make sure I covered this bit because of the question earlier. So as you can see here, we have your primary coming into heat exchanger, your secondary going out, trap sets, your condensate. So this particular one is air heating. So as you've got the air passing over the tubes that are inside, the elements that are inside, it's transferring the heat from the steam. So the heat is from the enthalpy, the energy is being sent into the air around it, and it's condensing into water. So the challenge you have with this is because it's at 1 bar G, you have a 15 meter lift, you have a back pressure of 1.5 bar. So the heat exchanger or this heating element will flood, especially when the control valve closes, because you have a higher outlet pressure or downstream pressure than you have upstream. So how we get around that? So you've got the temperature control system. So effectively you've got the heat exchanger here, as you can see, you've got P1, P2, Q equals UA, that delta T. So you've got the, I'm still doing the temperature thing, sorry. So you have the system there, the control valve meeting. So that's how you work out the loads for there. So I'm trying to get to phase 2. So heat exchanger flooding, so on the steam side, so it gives you reduced and an unstable heat output. So because the water has a different enthalpy to what the steam does, it's not related to pressure, as pressure temperature is related in steam. Gives you unreliable process times, so can extend the process time for heating. You get temperature fluctuations, particularly in these in the secondary media. Water hammer, because you've now got water in a system that's meant to have steam. Vibrations possible, so again, because of the water hammer, you're getting vibrations. And damage to the tube bundle. Corrosion, water is going to combine. It's going to be more corrosive on the system than steam. Product quality problems. So if you're not attaining the heat required for your product, for your media, you could get less quality, worse quality on the media that you're trying to heat. So I'm thinking more, so say on pasteurization of milk, those kind of things. So condensate removal. So as we have here, we have a pumping unit at the bottom of the heat exchanger. Still the air system here, control valve coming in at the top. So your primary is filling the air handling unit, so the AHU. But your secondary side, where you've got a vessel there to hold the condensate so you don't get any flooding. Down for your traps and your strainers into a pumped unit, which then sends the condensate back. The secondary side you can see into the pumped unit, which is red, is a motive steam line. So when you do get stall, when you get higher pressure on your upstream, downstream as you do upstream, the motive steam is designed to kick in, pressurize the line and remove the condensate. So any questions there?
There are no questions in the chat box.
Okay. So turf flow applications. So pasteurization, as we spoke about before. So it's the process in which packed and non-packed foods, such as milk in this case, or fruit juice, any kind of food, are treated with mild heat. So you're looking to effectively kill off any bacteria that's in there, to, as it says there, pathogens and extended shelf life. So the less contaminants you have in your food media, such as milk and fruit in this case, the longer the life you can keep it on sale for. It's widely used in the dairy industry, so pasteurization is common in milk, as many of you will know, and food processing industries to achieve food preservation and food safety. So we don't want to sell anything that has any pathogens in, we want to kill those off. Critical factors, temperature of process, contact time with the product, so how long we're heating it for and the temperature we achieve. So here, as it says, typically 10 to 30 tons. Between 70 and 95 degrees. CIP, clean in place. So it's a method of cleaning the interior surfaces of pipes. So your steam system or your secondary sides, you may quite often will flash your system or flood your system in the secondary to be able to, clear any bacteria, anything that might be living in those pipes. So temperature of the cleaning solution is a key factor. concentration of the cleaning agent, so the chemicals you're using, contact time with the cleaning solution, so how long that's in the system, pressure exerted by the cleaning solution, turbulence, so you need a turbulent flow to be able to break off any crustaceans, any scale that may be forming on pipes. Again, typically between 10 and 40 tons of water, and NaOH, which is NaOH. Wayne, remind me what NaOH is. It's caustic, isn't it?
Yeah, it's caustic.
Yeah, at 70 degrees. So a clean in place system, as you can see here, you have your heat transferred into a heat exchanger in this particular case. So we were talking about heat exchangers here. Heating up your CIP fluid and going into your tanks. So in this case, they're using buffer tanks, pre-rinse tanks and detergent tanks. So we're using that to heat. So clean in place system, CIP system. Many of these will look familiar to you guys, and you will see these in your sites. So bottle washing. Again, we would use it for bottle washing. So this is the method used to wash the bottles before filling. So especially in Africa in general, I believe we tend to reuse materials more than, say, the Western world. I noticed KBL places, big breweries, they tend to receive their bottles back, rinse them, wash them, remove the stickers, reuse them. So critical factors. Hygiene of the bottle, so need a high flow rate. Concentration of cleaning agent again, and water wasted quantity. So we don't want to waste, we want to save as much water as possible. Typically between 30 and 100 tons of water. And as you can see there. So pharmaceutical, I'll use a lot of heat exchangers for similar processes. So controlling the temperature of a product inside the vessels. So a lot of drugs, a lot of processes in pharmaceutical require a certain temperature, partly to cook the product, also to sterilize it. So critical factors here is hygiene, products inside the vessel, and temperature control. So it's very specific, very tight, the temperature ranges that are required in pharmaceutical industries. I'm keeping an eye on the time. So again, cooking. Yeah, so if you're using autoclave, for instance here, so an oven, using hot water in direct contact with the product, you need the steam in the jacketed of the vessel to maintain the temperature for the required period. So I'm thinking of a cooking pot or whatever else where you're transferring the heat into the convected into the water to be able to cook the item you have. Critical factors, hygiene, as it says here. Contact time with food, so you don't want to overcook it, and it needs to be a constant temperature. Dairy, we've already covered. So again, here is the hygiene, the product in contact to water and constant temperature. So this particular case is mozzarella cheese. So coffee, barley extraction, tea, we'll use it as well. So critical factors here again, product contact with materials, water temperature. Typically water at 100 degrees, heated in thermal oil with thermal oil. And marine, so sanitary hot water, galleys. A lot of these big ships will have some kind of steam boiler. And we'll need the steam for the industry there, so there is a heat transfer there too. So final points before we go into the Q&A. I think I'm on time. Behind every heat exchanger, there are several calculations. So again, we can talk, if you contact us directly, we can talk deeper with those. Turbulent flow improves the efficiency, so it gives you better heat transfer, and it makes the units smaller and cheaper. Big flow rate, big shell diameter, so there is a corresponding size that's required there. And high on the process fluid, long heat exchanger. So the longer it needs to be in contact, the longer the heat exchanger needs to be. Co-current units can control better at very, very low temperatures. e.g. delta T's even, so temperature variance. And all temperatures are required for sizing. Duty only is not enough. So you need to know your primary, your secondary temperatures. If it's a batch process, all relevant data is required for sizing. So effectively, if you're doing a batch, it's more data that you need to know the temperatures of the batches and so on. So on to Q&A. Is there any questions?
We've answered all the questions that were published. At the moment, there's no questions unless some come through.
Okay. So while we wait for see if there's any questions, I'll just leave you with the last slide, the second from last slide. So in-depth training, as it says here from our webinar, so these are always meant to be kind of a light touch on the subject, but you can request it through our opcos, our offices, our local offices, and we can do online training. We can conduct it at your business premises, and we offer free online correspondence courses, which you can find on our website. We also supply a wide range of engineering books in PDF form. So we have our steam and condensate loop book and our engineering booklets. So the particular one is the metric data book. We do a series of them. And our contact details. So you've heard from myself. Wayne's been instrumental in helping me with the questions. Yep.
There is one question, sorry, that we never covered, and I'm not sure. It says, please explain purpose of turning plates in PHE. I personally never heard of that.
Neither had I. They have to be in a specific direction for the plate heat exchange to work properly. I can understand why you would think you could, because they almost look identical, but they are set in a certain pattern. I think the ridge details on each side of the plate are very important on the direction of the plate heat exchangers, so you wouldn't turn them as such. You may rotate them from the end to the well, from the front to the end, but you wouldn't rotate the direction. I don't know if you know any more on that, Wayne.
No, I'm not aware. I just know that the end plates are slightly different. But as you say, the configuration is such that it needs to maintain its integrity as it was built. You know, I've never heard of, unless we're misreading the question of turning plates in a PHE. This is an anonymous question, so maybe the anonymous can just explain a bit better and we can try and help further afterwards. There's some further questions that have come through. Please, would you share the material that's been requested? We can do that. And yeah, we go. Turning plates that changes direction in a multi-pass PHE. Changing from one pass to a two-pass.
I'm not so familiar with that.
Yeah,
I can,
myself.
you know, if you get in contact with us directly, send through your question. We don't always know everything, so we can go off. We can ask our colleagues, do a bit of reading, and get back to you.
I think we'll have to come back to that one. Yeah, I'm also unaware of that. Different pass, different plates.
So any other questions?
No, none so far. Seems like we're all good.
Okay, so I want to thank everyone for joining. It's always a pleasure to present to you guys. I hope we answered your questions, and if not, please reach out to us. I mean, I've left a slide that's on show at the moment purposely for longer, so you have all our direct contact details. And please feel free to use them. We love to have these conversations with you. The more difficult, the better. We like to use our brains. So please feel free to use them. And if that's everything, that's all I have.